All right, so here's an analogy we want to think about. So imagine I've got some tennis balls, and let's just say for the sake of argument that they're about 0.1 kilograms. If I want to take a tennis ball and lift it up to the top of this box, I've got to do work. So I'm applying a force, and a force applied times the distance that it's applied tells you how much work you have to do. So to take a tennis ball and to lift it up here, I've got to do work. Oh, that's a lot of work. And I can put it up there. So I did work. I ate my Wheaties this morning. I had lots of energy ready to go. And I transferred that energy to the tennis ball. So I did work. I applied a force. The force I applied was because gravity tended to pull the ball downwards, so I had to apply an upwards force. And after doing work, the tennis ball is at the top of the box now. So if I applied a force of 1 Newton, and I apply that force for a distance of about 1 meter, then I did 1 joule of work. The question is, where is the energy? I transferred energy. The energy went from me, from my muscles, to the tennis ball, but what form does the energy have now? Well, you'd say it has potential energy. It has stored energy because of its position in a gravitational field. This ball can do work for me now. If I were to give it a little nudge, I could get that energy back. First, it would turn into kinetic energy, and after kinetic energy, when it got to the bottom, it was moving fast. I could take that kinetic energy and I could turn it into any other kind of energy I wanted. I could have it maybe go down a ramp and smack a car, make the car go. Or I could make it spin a paddle and generate some electricity, but I have energy. So when the ball is up here, it has energy because of its position in a gravitational field. If somebody were to turn gravity off, if gravity were to just simply switch off right now, this ball would have no energy. It wouldn't do me any good because if there was no gravity, I would roll it off and it would just sit here. It wouldn't start accelerating downwards. So the ball has energy in its gravitational field, we say. All right? So because of gravity and the work I did against gravity getting it there, it has energy. And so this ball right here has 1 joule of energy, about. I could do it again. There we go. How much energy do I have stored now? Well, 2 balls, 1 joule each. I have 2 joules of energy, or 3 joules of energy stored and ready to go. All right? So one of the things we do when we talk about electrical energy is we don't just talk about how much energy we have. Right here, I have 3 joules of energy stored and ready to go. But when we talk about electricity, we talk about how much energy is there per ball. So if you say, well, how much energy is there per ball? The answer is there's 1 joule per ball, and there's 3 balls, for a total of 3 joules of energy. Okay? All right, now, what if I had a different box? So here's a different box right here. And I can do work, and I can put balls at the top of this box. So I can put a ball here. Now, this box is only about half as high. So this energy is not as much as that energy. So this energy, there's about half a joule of energy here, because it only took half a joule of work to get a ball there. Okay? So if I put a ball there, and I get a couple more, and I put a ball there, and I put a ball there, and I'm going to take these 2 off just for purposes of illustration. Okay, so right now, this ball has 1 joule of energy. This ball has half a joule of energy stored in a gravitational field. Which of these sets of balls, the high or the low set, has more total energy available to me? I mean, if you had to do a job and you want to know which one has the most energy, would you rather have 1 ball with a joule of energy or have 3 balls, each with half a joule? Well, clearly there's more energy here, okay? So we have to differentiate between the total amount of energy we have and the energy per ball. Here we have 1 joule per ball. Here we have half a joule per ball. The energy per ball is only half a joule. The total energy here, though, the total potential energy we have available is 3/2 of a joule, or 1.5 joules, because we have 3 balls at 1.5 joules. Here we only have 1 joule total. all right? So there's a difference between the amount of energy we have per ball and the total amount of energy we have available. Here, we have 1.5 joules of energy per ball, but we have 2 joules total because there's 4 balls. Here we only have 1 joule. 1 joule is not nearly as much as 2 joules, even though the energy per ball here is higher, okay? When we talk about electricity, we're not going to talk about potential energy all the time. We're going to talk about potential energy per charge, and that's why it's important to understand this distinction, okay? Okay, so that's my gravitational example. Now let's think about it in terms of electricity and charges. So now, forget gravity, and just imagine that over there is a conductor. It's a piece of metal or something, and I've got a whole bunch of charges here. I have as many charges as I want, okay? So these are not tennis balls anymore, these are charges. Now suppose I want to put one charge over there on that piece of metal, okay? It's not very hard to do. I can just roll that charge over there and stick it on the metal, and there's no trouble with that. But when I have a second charge, these two charges, think about electrons, these two electrons are repelling each other, which means if I were to let this go, it would zoom away from that guy. So in order for me to put this over there, I have to shove it. I've got to push it. I've got to do work. And when I get it over there, the two of those guys are going to spread out as far as they can. Okay? They're repelled. Now, if I want to put another electron on there, I've got to push even harder. I've really got to do a lot of work. And when I finally get it here, where did the energy go? I did work. I pushed that ball, that charge, onto that metal plate, and the energy is now stored. We say that the charges have potential energy because of their position, because they are repelling each other. And so I could take more and more charges and keep pushing them on. And as I push them on, they would spread out. And what I would have here is a whole bunch of charges that are all repelled. And if given the chance, if this guy was allowed to leave, if there was a path for him to leave, so this is a piece of metal in our illustration here. If there was a path for this guy to leave, he would go zooming away. And as he went zooming away, he could do work. He could go through your electronics and make your screen turn on. It could make your hairdryer hot. It could power a light bulb. It could do all kinds of things. It has energy, all right? So we say that an array or a collection of charges, because of their mutual repulsion, store energy. And so we would say that there is energy stored not in gravity or a gravitational field, but because of the electrical configuration, because of the electric force. There's energy stored in the electric field, we say, okay? And that's how we store energy electrically. We put a whole bunch of charges together that don't want to be there, and as they escape from one end of the battery, for example, to the other end of the battery, they can do work. They can give their energy back, and you can use it in useful ways. And then when you want to recharge your battery, so when you use your battery, these charges escape one at a time, and as they escape, they do work. They power your phone. And when you need to recharge your phone, you've got to shove them back on there. You have to do work. And the work you do is energy you expend. And now at the end of the day, you're tired, but your battery is recharged. All the charges are ready to go. There's a lot of energy stored. We call this electric potential energy. So electric potential energy is the energy stored in a configuration of charges. Okay? All right, that's going to help us when we try to understand what voltage is. All right, so we kind of looked at an analogy with tennis balls, thinking about gravitational fields. So the part that we really need to understand for this is that if I take a charge and I want to push this charge onto a metal conductor that already has charges on it, that is going to require work. The work that I do is the force times the distance that I push it, and that work is energy that I expend. And so when I get it over there and it's on the charge, I have done work. And so now that energy, the energy I transferred, is stored in the electrical configuration of these charges. In this case, they're positive charges, but usually they're electrons. Okay? So here's sort of the important part of the story. We can store energy in an electric field. The energy that we store in an electric field is called the electric potential energy, just because these charges are all ready to go. They're storing energy, and if you connected them with a wire, for example, to something, these charges would zip off there, all but the last one, and in doing so, they would do work for us. We could get our energy back. This electrical potential energy that we're talking about, the energy we're storing on the charges, is just energy that we've been looking at all year, and it's measured in joules. All right, so those are the key points. So when we talk about electrical potential energy, we're talking about the energy stored with charges. So a related topic is voltage. And so the question you might ask is, here's a whole bunch of different kinds of batteries. What is the difference in all these batteries? So that's kind of what we're going to look at now. So voltage isn't quite energy, but it's related. So do you remember in the analogy when I talked about how much energy each ball had? That is like voltage. We are going to define voltage as the amount of energy that is stored per unit of charge. Okay, so not the total, voltage is not the total energy, it's the amount of energy per charge. So in the tennis ball analogy, on the high box they had 1 joule per ball, and on the low box they had half a joule per ball. That joules per ball is basically like voltage. It's the energy stored per unit of charge. Okay? So voltage is going to be defined as the potential energy that is stored divided by the number of charges that it's stored across. All right? So if I have 2 joules of energy stored in 2 charges, that's 1 joule per charge. That's 1 volt. All right? So this is a good thing to put in your toolbox. You can pause the video and get this jotted down. The voltage is defined as the potential energy that is stored divided by the charge in which it is stored. The potential energy is measured in joules. The charge is measured in coulombs. And so a joule per coulomb is the unit of voltage, which we call the volt. So a volt is a joule per coulomb. 10 volts is 10 joules of energy per coulomb of charge. So here's an example to kind of help us wrap our heads around this. This is a D-cell battery here on the left, and it's used for incandescent flashlights in the old days. By old days, I mean back when you were born. Nowadays, we don't need quite such big batteries because we have really high efficiency LED lights, flashlights. But back in the old days, we needed bigger batteries. So here's a D-cell. This typical D-cell holds about 1,500 joules of energy. And that energy is stored in about 1,000 coulombs of charge. So if we want to know what is the voltage of this battery, we could say how much energy is it per charge. So we have to take the energy, 1,500 joules, divided by 1,000 coulombs, and that gives us 1.5 joules of energy per coulomb, or we say 1.5 volts. So this is a 1.5 volt battery. Now, on the other hand, this is a AAA battery. So this is what's in your calculator if you have a graphing calculator that has batteries. This battery here only has 150 joules of energy. It has not nearly as much energy. That 150 joules of energy is stored in 100 coulombs of charge. So if I ask how much energy is stored per unit of charge, I could take 150 joules divided by 100 coulombs, and again, I would get 1.5 joules of energy per coulomb. So in this case, we also have a 1.5 volt battery. So the 1.5 volts does not tell you how much energy the battery has. It just tells you how much energy there is per charge. In this case, the battery on the right, we had 150 joules. The battery on the left had 1,500 joules. It has 10 times as much energy, but they have the same energy per charge. And the reason we talk about energy per charge is because it's the voltage that determines how hard the electrons are pushed through a circuit. When we talk about circuit analysis and we look at simple circuits later, we'll talk about voltage as being the push on the electrons. So when we're talking about circuits, voltage and energy are very close related, but they're not quite the same thing. So let's just look at two example problems that would go with the problem set you're going to work on. Let's suppose I have a Van de Graaff generator, so when we ever get back to class, whoops, we're not getting back to class this year, so we can't really show you, but this thing here spins and the dome gets a charge on it, and you can touch the dome and shock yourself, and it's a whole lot of fun. But let's say that 1.2 joules of energy is transferred to the charge on this dome. So the belt carries charges up here and dumps them on the dome, very similar to rubbing a balloon on your wool sweater, and that produces charges up here. And the total amount of energy transferred is 1.2 joules, and that 1.2 joules is stored in 2.5 microcoulombs of charge. And I want to know, what is the voltage of the dome with respect to the ground? What is the charge, okay, per coulomb? So here's what we know. We know the potential energy stored in the charges is 1.2 joules. And we know the charge is 2.5 microcoulombs, or 10 to the negative 6 coulombs. So to find the voltage, we simply have to evaluate the potential energy, the energy that's stored, divided by the charge. That's going to be 1.2 divided by 2.5 times 10 to the negative 6 coulombs. And assuming you group your denominator correctly, you're going to get a really large number here. You're going to get 480,000 joules per coulomb. And so that's 480,000 volts. So the voltage on the charges here is quite large, and that's what makes them jump across the air and sting you on the finger. So that's an example of how we use this expression. There's 1.2 joules divided by a really tiny amount of charge. So if you had an entire coulomb, you would have 480,000 joules of energy in a whole coulomb of charge. All right, one more example. Suppose we have a 9-volt battery. So this is what's in your smoke detector, and you've got to keep changing that every year. And during the course of a year, when it's being used, it can produce 1,400 coulombs of charge. So from one end to the other, through the circuit of your smoke detector, over the course of a year, 1,400 coulombs of charge will flow. And I have 9 volts. That means I have 9 joules of energy per coulomb. And so I want to know how much energy there is there. So I'm looking for the energy that's stored in the battery. There's nothing on the battery that actually tells you that. You know the charge is 1,400 coulombs, and you know the voltage is 9 volts. And so to figure out how much energy you have, you're going to have to solve this equation, voltage equals potential energy divided by charge. You have to solve that for the potential energy. That's not too hard. Multiply both sides by Q, and you get the potential energy as V over Q. Plug in your numbers. Your voltage is 9 volts. Your charge is 1,400 coulombs. I'm going to write this one more time just to show you what happens to the units. Remember, a volt is a joule per coulomb. So you have 9 joules per coulomb times 1,400 coulombs. This coulomb cancels with this coulomb, and your answer is left in joules. So it turns out you get 12,600 joules of energy stored in this 9-volt battery. And a good engineer would never report an answer of 12,600 joules. They would say 12.6 kilojoules. So when you're solving the problem, just keep an eye on the answer and what units are expected. You might need to do a conversion there. Okay? So what we're going to do today in this lesson is just practice solving some problems involving voltage, V, the potential energy, PE, and the charge, Q. Okay? So find your problem set and get going.